Hi class, welcome to Is451. I'm Professor Fahmi Jalani. We'll be covering chapter 6 for this lecture 6, errors, error detection and error control. Okay, let's begin. As you all know, in most communication, there are bound to be noises, and with this signals and data are being corrupted and lost. And having said that, there has to be a check system during the transmission. And so when there's an error, there's need to be a system to detect it. Okay, and how are you going to resolve it? So let's first take a look at some of the causes of error. First, we have white noises. Okay, technically these are terminal or Gaussian noise. Okay, as we look at the figure here, A, we have a perfect square wave, little noise introduced on B and much noise on C, and the signal get disrupted. Next we have impulse noise. This is very destructive, where signal disrupt, or when you have a large spark on it. Okay, it could be a power source or lightning strike. Okay, and because of this, the data cannot be recognized, and it's distorted. So some example we have here. Here you see the signal, and especially when the noise is being introduced, so bits are lost. Next we have crosstalk. Crosstalk is basically when you can hear another person's conversation from another line. Sometimes you are able to hear this, especially in on wire lines, or when the transmission is very close. There are times when you can hear it when you are calling the operator, but that is basically when there's another operator nearby. Next we have echo. The word explains by itself, where there's a feedback sound, usually occurs in coaxial cable. Next we have jitters. Jitters basically small irregularities, okay, in digital timing, as you see from the figures. Next we have delay distortion, when the speed is fast or either slow. Okay, it's propagated basically. And also we have attenuation, when the strength is not strong enough to transmit across the medium, and it diminishes as it travels. Next we see some of the preventive measure. Okay, to prevent this, basically in physical layer we have to proper shielding the cable from interference, equalization, telephone line condition, means they are replaced as being used across the time frame. Proper repeater need to be used so that signals are being amplified as it travels for over a distance. Okay. The table here shows error prevention, for example, white noise, install filters, okay, impulse noise, same thing as white noise, crosstalk, proper shielding, echo, proper termination of cable where signals are not repeated again or bounce back. Jitter, basically to use better electronics repeaters so that they're synchronous. Attenuation, install amplifier, I mentioned just now, over a long distance. As for error detection, despite all the measures we have, okay, we still need other techniques, for example, parity check, arithmetic checksum, and CRC or cyclic redundancy checksum. So let's take a look at the first one, parity check, simple parity. Here, if you look at the example, we have even and odd. The first one is even parity. So the second one sends using even parity. Okay. If you look at the end, there is 0 and 1, the digit. Okay. Here we have a longitude parity. Row 1 we have parity 1, okay, followed by 2, 3 and 4 all parity 1. As you compute, okay, from 1 to 4, okay, here we have 0. Here because it's odd, we have 1. Even 0, even 0, odd 1, odd 1, odd 1, okay, and even 0. And those are the parity. So in the event there is error, okay, so in this case second and third bit for row 1 and 2, okay, longitude error does not detect the error, okay, longitude. So in this case this is even, this is odd, okay, second one is odd, the third one is even, okay, and follow on. Okay. So basically simple parity and longevity does not catch all the errors. So for simple parity, it only catches odd number error, and longitude requires too many checking. Right. Next, we take a look at arithmetic check used by TCP/IP. Over here we have basically the sum. Here is simplified example, 56, 72, 34, 48, and we have the sum is 210. So we bring down the number 2 and we compute, we get 12. So this is check at the end of the transmission line. So the receiver performs same conversion and summing and compares new sum. So it's a bit more complex. Next we have CRC, okay, cyclic redundancy check. It's more like a packet thingy. It uses polynomial arithmetic. attached to the message, okay, and it's divided. We'll take a look later on. How is it done? Here, for example, we have the polynomial CRC12, 16, CCITT 32.1, okay, and ATM. So for single bit, it's 100% error detection performance till an error bus all the way to length less than r plus 1. So when there's is error detected, basically it's not going to do anything but return the error transmitted. Okay. So if there's an error, the packet is tossed out. Okay. A new packet is sent again. Okay. Once an error is detected, an error message is returned to the transmitter. So it will stop and wait for the error control. Okay. Or sliding window error is performed. We will take a look at the next slide to have a clearer view. First, we take a look at the stop and wait, station A and B. Right? If an acknowledge is received from station A, sending data to station B, okay, then station A will send another data. In the event there is no acknowledge, the data will be resent from station A to B. Okay. Next, we have sliding error control. Okay, this technique assumes that multiple frames are transmitted at one time. Yeah, it depends on the window size. Okay. In this case, there's 3 packets being sent, so they acknowledge 3 here. Okay. Next slide, we have this is basically older sliding window. Okay, station A to station B. Here we have this that the acknowledge is not always sent after each frame is received. Okay, bytes are sent 800 and then another 400 to 800. Okay, and it's only acknowledged at 801. So in TCP/IP rule 1, okay, receiver just receive packet and want to send own data. Piggybacks a lot and acknowledge along the data. Okay, receiver 2, no data return. Has acknowledged last packet with 500 millisecond. Rule 3, receiver has no data to return, just acknowledge. Okay, no packet or send acknowledge. Let's take a look at the diagram. Right. Here we have station A and B. First one is rule 1, okay, where the packet is acknowledged at 351. There's a piggyback. Okay. It's basically using another data to send back. Rule 2, okay, 2 sets are being sent. Okay, it waits for 500 millisecond. Okay, and then send and acknowledge. Okay. Rule 3, the receiver will wait for 500 millisecond and then return no packet, send and acknowledge. Okay. So what happened if the packet is lost? you only acknowledge it even after the second package is received, okay, in order for station A to send back again. So what happen if no acknowledge? Okay, station A will resend packet again. Next, we take a look at correct the error. So for transmitter, a lot of redundancy. It's so called forward error correction, okay, or called Hamming code. These are basically check bit. Hamming code 8-bit character, number C8, C4, C2, and C1. Data bit B12 all the way to B3 without B8 and B4. So place the bit in the following order: B12, 11, 10, 9, check bit 8, B7, 6, 5, C4, B3, C2, and C1. So example, okay, C8 will do parity check for anything 12 to 9, and C4 will do anything between 12 to 12, B7 to 5, and C2 will do 11 to B3. C1 will do B11 to B3. Okay. Let's take a look at the next slide. Will be much clearer. Here the Hamming code. Okay. C8, the check from 12 to 9. Okay. C4, 12, B7 to 5, C2, 11, 10, 7, 6, and 3, and C1, 11, 9, 7, 5, and 3. So the sender will take the 8-bit and generate a 4 check bit, okay, like we seen in the diagram previously. So here's C8 check for the bit 12, 10, 12, 11, 10, 9, 8. This would cause a parity error. Okay, and for C4 and C12. Okay. So the example here, B9 flips. Okay, so it will cause a parity error, okay, on the ninth position, for example. And so FEC is commonly used in radio signal and digital television or read Solomon or terrace encoding, also 4D primes. Okay. So that's pretty much for error detection. If you have any question, please email me or set an appointment. I'm pleased to see you. So please stay safe and thank you very much. Bye bye.